Okay, let's get started. Hello, everyone. My name is Johan Jo. I'm one of the TAs for this course, and I'm also a PhD student at the Language Technologies Institute. Today's lecture is going to be about sentiment analysis and computational argumentation. So let's start with some example. So if I say everyone should go vegan, then let me ask you some questions. Is this an objective fact or is this my personal opinion? So who thinks this is an objective fact? Who thinks this is my personal opinion? Good. Am I expressing any positive or negative attitude towards some topic here? So, for example, am I expressing a positive or negative attitude toward veganism here? Possibly. Positive? Yes. Okay, the last question. Is this an argument? Who thinks this is an argument? Okay, who thinks this is not an argument? Can someone explain why this is not an argument?
Because no argument is made, like it's just a suggestion that doesn't explain why.
Okay, it's just a suggestion and doesn't explain why. I think you hit the point. If I continue to say, because vegan diets are healthier than eating meat, then now it becomes an argument. So many times what we say is not merely an objective fact, but instead it often expresses our attitudes or opinions towards some topic. So roughly speaking, analyzing what attitude or opinion does it express is related to sentiment analysis, and analyzing why do I have that attitude or opinion is related to argumentation. So these two are the main topics we're going to be covering today. So the first part of the lecture is about sentiment analysis. In 2011, there was this paper published. They said, Twitter mood predicts the stock market. So in this graph, the blue line is the Dow, a stock market index, and the red line is their mood score, specifically for the mood calm. They extract it automatically from tweets. And they argue that this calm score can predict the ups and downs of this calm score can predict the ups and downs of the stock market. So we will see how they computed this mood score soon. But it is important to note that the sentiment analysis techniques are widely used by companies and organizations for practical purposes. So in the first part of the lecture, we're going to be covering what exactly is sentiment analysis. Is it just like classifying positive and negative? And how can we do sentiment analysis? And we're going to see two approaches, lexicon-based approach and machine learning-based approach. Okay, what is sentiment analysis? Based on Wikipedia, sentiment analysis, also known as opinion mining or emotion AI, refers to the use of natural language processing, text analysis, computational linguistics, and biometrics to systematically identify, extract, quantify, and study affective states and subjective information. So it sounds like sentiment analysis uses all these tools to analyze two things, affective states and subjective information. But what are they? So according to this theory, there's 5 different types of affective states. So emotion is a brief and intense episode of organic response to the evaluation of an event, like angry, sad, joyful. In contrast, mood is more enduring and less intensive predominance of subjective feelings, often without even apparent cause, like cheerful, gloomy. On the other hand, there's interpersonal stance, which is the affective state occurring in the interaction with another people. And it colors the interpersonal exchange of that situation. So I feel that this person is polite, or I feel that this person is too cold, and so on. And attitudes are enduring beliefs and predispositions towards specific objects or persons. So for example, I like this phone, or I hate this phone, or I value this phone, and so on. Lastly, personality traits, also called affect disposition, is stable personality dispositions and behavior tendencies, like feeling nervous or anxious. So I think today's sentiment analysis systems cover all these different types of affective states. Okay, then what is subjective information? So subjective information can be broken down into judgment and personal belief. So judgment or evaluation, according to the definition of the dictionary, is determination of the value, nature, character, or quality of something or someone. So if I say, this movie is garbage, or the battery lasts less than 5 minutes, unfortunately, then I'm expressing or I'm evaluating the movie and the battery quite negatively. Then we have personal belief, something like, I don't think the earth is round. So this is definitely an opinion, but I don't think many sentiment analysis systems are interested in this yet. But this is very important for argumentation systems. Okay, so we can see some generic structure of sentiment information. So one of the facets is the holder or experiencer of the affective state or opinion. And it's usually the speakers themselves, if not stated otherwise. And there's the target of the affective state or opinion. And there's the type of the affective state or opinion. And we can use all different kinds of emotions, but in today's NLP, this is often simplified as just positive, negative, and neutral. And there's the claim, which is the text that contains the affective state or opinion. So let's look at this example at the bottom. I say their new ice cream is awful, but Chris loves it. Then there's two pieces of sentiment information here. So in the first piece, the holder is the speaker, which is me. And the target of the sentiment is their new ice cream, and the type is negative. On the other hand, in the second piece of the information, the holder is Chris, and it has the same target, but Chris has a negative or a positive sentiment toward this ice cream. So this is kind of generic structure in sentiment information. And most sentiment analysis systems focus on these two: target, what is the target, and what is the type of the sentiment. Okay, based on this definition, let's look at how we can do sentiment analysis. So first, we're going to see the lexicon-based approach. Let's start with a simple example. If I say I'm loving it, whatever it is, am I expressing positive sentiment or negative sentiment toward it? Positive? How do you know that? Because love is a positive word. So if I use the word love, if I say love something, I love something, then it generally has this consistent sentiment that I have some positive sentiment toward the target. So based on this idea, there's some words that have consistent sentiment whenever they're used. And there's some lexicons that compile these words for different categories. So for example, the general inquirer and the linguistic inquiry and word count, they're used by psycholinguists, and they have different kinds of words like positive, negative, hostile, social, causal, and so on. And the MPQA subjective lexicon has positive, negative, and neutral words, but they also annotated each word as strongly subjective or weakly subjective. And Senti WordNet is WordNet synsets automatically annotated for positivity, negativity, and neutrality. But it is important to note that this sentiment information is only tendency, and the actual sentiment of a word in real text is highly context dependent. Okay, those were some general words that have consistent sentiment. But if you look at some words have different sentiments, even opposite sentiments, depending on what those words modify. So in this example, in a restaurant review, if I say my dish was served hot, then I'm evaluating this restaurant quite positively. But if I say in a speaker review, it gets hot very easily, then the same word hot becomes or expresses negative sentiment in this situation. And similarly, other words like cheap or loud can have quite opposite sentiments depending on the target. So, okay, it is good to have some lexicon, but how can we use or build a lexicon that have words that are specific to certain targets? So building such a lexicon manually is very time consuming and is very expensive. So can we automate this process a little bit? So one possible way is to look at their co-occurrence with other words. So in restaurant reviews, for example, you'll see quite easily people saying like, I was impressed the staff was very friendly, or I was disappointed that the restaurant takes cash only. So by looking at how often a certain word occurs with some general positive or negative words near to each other, you can infer the sentiment of a certain word in the specific domain or specific target. So then how can we quantify co-occurrence between words? So we can use something called point-wise mutual information. It is defined by this formula. So what it means is basically the difference between the probability of word 1 occurring when word 2 is already observed versus the general probability of word 1 occurring. So let's think about two extreme cases. If word 1 and word 2 are completely independent and they're not related to each other, then the PMI score will be very low. On the other hand, if those two words always occur together, then the PMI value will be very high. So our basic idea here to build some target-specific lexicon is to choose words like adjectives that have high PMI scores with some general sentiment words. But then how can we get those general sentiment words? So there's different ways. Of course, we can use some sentiment lexicons that we mentioned before. But we can be a little bit more creative, like we can use some emoticons or emoji, or we can use some hashtags in Instagram or Facebook or Twitter. So these some of the possible ways to get these general sentiment words. Okay, now we have some lexicon, but you may feel that, well, this lexicon is maybe too small to apply to my data. So somehow I want to expand this lexicon, including more words. So how can we do this automatically? So one of the most straightforward ways is to use synonyms and antonyms. So fast is synonymous to expeditious, rapid, quick. So they're likely to have the same sentiment in a certain context. Whereas calm is opposite to agitated, angry, or inclement. So they're likely to have different sentiment. So we can use this information to expand your lexicon. So the authors of this paper used a little different approach. So they used conjunctions and or but. So the main intuition here is that if two adjectives are conjoined by a conjunction and, like this laptop is fast and quiet, then they're likely to express the same sentiment. And if two words are conjoined by but, then they're likely to express some different or opposite sentiments. So they built this graph based on a huge corpus of documents. So in this graph, each node is an adjective, and the edge between two nodes is the probability that the two words have the same polarity. So how did they calculate this probability? They used some machine learning approach here. So they calculated this probability, or they predicted this probability based on the counts of different conjunctions between them in the data. So they trained a model to predict this probability using some smaller corpus. So once you have this graph, they basically applied a clustering method. So they categorized each word into either positive or negative based on the distances between these words. Okay, so you might think, now we are living in the era of machine learning. Who cares about lexicons? Well, at least these people did, and they used pretty simple method to extract the Twitter mood scores. So they started with a small lexicon. This lexicon is from the profile of mood states. It has only 72 terms for 6 mood types. And then they expanded this lexicon using a huge corpus. So they included 964 terms for these 6 mood types. So basically for each mood type, they expanded the words they included more words, and each word is assigned a co-occurrence score, which indicates how similar this word is to the words in the original lexicon. So given this expanded lexicon, they calculated the score of a tweet for a certain mood, like tension, by just summing the co-occurrence scores of the words that occur in that specific tweet. And the mood score on a certain day is simply the average mood score of the tweet on that day. So that's how they calculated this mood score. It was quite effective. Okay, now let's move on to the machine learning approach. To apply machine learning for sentiment analysis, we first need some labeled data. So how can we obtain this labeled data? There's several ways. First, we can just collect already labeled data. And a good example is Amazon reviews. You have some reviews, and all of these reviews have some star ratings. So you can simply use them. But it can be problematic because each review usually has mixed opinions. And just one star rating may not be enough to express all these nuanced opinions. On the other hand, reviews in TripAdvisor are pretty good because you can rate for different aspects of a hotel. So you can use this data also. And this approach is very cheap. You can just scrape the reviews, but you can cover only limited domains. On the other hand, you can annotate your own data as you need. So in the first example, they annotated certain words with positive, negative, and neutral. In the second example, they annotated individual tweets in terms of the target of the sentiment and what's the sentiment toward the target. This approach, you can annotate any domains, but it's very, very expensive for humans to annotate all this sentiment information. So you can take some approach in between. So you can use some noisy labels. So you can use some emoji, or you can use some emoticons, or you can use some hashtags as some noisy labels. So this approach you can apply to many domains, and it's pretty cheap. But the problem is it can be quite inaccurate. But surprisingly, many researchers use this approach to label their own data. Okay, now that we have some labeled data, now we should decide the class type and classifier. So the simplest case is just binary classification, whether a review is positive or negative. So in this case, what kind of model can we use for binary classification? Naive Bayes, okay. Also, yes. Logistic regression, good. So we can use logistic regression or naive Bayes. If the output value is continuous, something like 1 star to 5 stars, then what classification methods can we use? If it's a continuous value. Okay, we can use some linear regression here for continuous values. What if there's more than 2 classes? So this is called multi-class classification. So let's say there's positive, neutral, and negative. Then you can choose from several approaches. First, we can just do 2-step binary classification. So we first classify between neutral and non-neutral. And for non-neutral instances, we can do positive versus negative. Or we can use the one versus rest approach, which is basically training a binary classifier for each class. So positive versus others, negative versus others, neutral versus others. And we simply choose the decision of the classifier with the highest confidence score. Or there's some models that by nature support multi-class classification, something like neural network, decision tree, or support vector machines. So we're going to see some examples later. Okay, last, we need some evaluation metrics. So for the binary classification, if the classes are balanced, we can simply use accuracy. But if the classes are highly skewed towards some class, like negative, then we can choose the minority class, which is positive in this case, and we can calculate the precision, recall, and F1 score. And similarly, for multi-class classification, if the classes are balanced, we can simply calculate accuracy. But if they are skewed, we can calculate something like average recall, which is the average recall for each class. So average recall basically means the average percentage of instances that are correctly classified for each class. So in your last assignment, we're using this average recall as the main metric. If the output value is continuous, then we can use mean absolute error, which is just the average distance between the true score and the predicted score. So if those two scores are close to each other, then you will have smaller mean absolute error. Okay, now let's look at some real examples of some classifiers for sentiment analysis. So the first example, they use some handcrafted features. So the task here is to classify the sentiment of subjective lexicons in the MPQA corpus into positive, neutral, and negative. So these subjective expressions, they're already pre-selected by humans. So in this example, our task is to predict the sentiment of these expressions in bold. So they logically use 2-step approach. They first classified neutral versus non-neutral. So they used all these features. So you don't have to memorize all these features, but it'd be nice to see what kind of features you can use other than just unigrams, bigrams, and POS tags. And after they classify neutral versus non-neutral, they classified non-neutral instances into positive and negative. So they use some features again, which are similar to the previous features, but not exactly the same. Again, it'd be nice to see what kind of features they used and why that they would be helpful. Okay, and then they use just some standard classifier using these features. Now let's look at some neural net-based approaches. So I hope this part will help you a little bit with your last assignment. So the first example for neural net-based approaches is multi-layer perceptron. So here in this picture, each gray box is a vector. So X is the bag of words vector for the instance. And this vector is multiplied by a weight matrix WH, and it outputs another vector H. And this vector is again applied or multiplied by another weight matrix, here WZ, and it outputs the vector Z. So you can increase the number of layers arbitrarily, but it's important to note that the final or the output layer has the dimensionality equal to the number of classes in your task, which is 3 in this case. So then how can we use or interpret this the output layer vector z? So now we define y hat, which is the softmax of z, is basically taking the exponential of z and then normalize it. Then the elements of y hat sum to 1 because of the normalization. And then we can interpret this vector as the probability distribution over the 3 classes. So the goal of training the model here is to make this vector as similar to the true y values as possible by finding the optimal weight matrices y, xh, and xz. So that's the goal of the training. But if we want to optimize these matrices, then we need some objective function, or we need some loss function. So given true y, which is an one-hot vector, so if in this case, if the instance has the true class positive, then the y becomes 1, 0, 0. So given this true y and predicted y hat, which is the probability distribution, the loss for this instance is calculated using this cross entropy, which is defined by this formula. But what it basically means is that the cross entropy decreases as your predicted probability for class C is getting closer to the true y value for class C. So you're optimizing this function to train your model. And in the assignment, you're asked to output some predicted classes for individual instances. Then how can we get those classes? You can simply look at the output vector z and then choose the dimension that has the highest probability or highest value, because that dimension is the class that has the highest probability for y hat. Okay, so next example is a recurrent neural network. So for this approach, we have an RNN cell, which is a small network that takes 2 vectors as input and outputs another vector. So we apply this RNN cell for individual words sequentially. And then we take the final output of this RNN cell, which is H5 in this case, and we use some similar optimization technique to learn all the weight matrices in the RNN cell. So the good thing about this approach compared to the previous one is that it considers or accounts for the order of words. So when you apply this RNN cell to a certain word, it already has some contextual information of the previous words. So for example, when you apply RNN to friendly, it already has this information that the previous word was not. So hopefully it might process the negation properly. The last example is similar, but it's called recursive neural network versus recurrent neural network. So recursive neural network is more general, and it can be applied to any structure, whereas recurrent neural network is usually applied sequentially. So the authors of this paper first parse the sentence into a binary tree, and they apply this RNN for every non-terminal node. So the idea here is that the output value of an RNN at a certain node contains all the sentiment information of the subtree. And using this approach, we can get some interesting results. So if you look at this sentence, the top node in the green area, the output of the RNN was predicted as positive because of the subtree. But when this subtree was combined with the negation on the left, which is in red, then all of a sudden, this RNN switched sentiment to negative because of this negation. So if you look at the output of this RNN for each node, then you can do some interesting interpretation of like what the model thinks about the sentiment of some subtree. Okay, so this is the first part of the lecture, sentiment analysis. Do you have any questions so far? Okay, clear? So let's move on to the second part of the lecture, which is computational argumentation, which is very exciting. Okay, this is the map of the United States from an article. And the blue states here on this map represent the states that use some automated essay scoring systems for any standardized tests. So you can see from this map that almost half the states use some sort of automated systems for scoring essays on standardized tests. And this article has this title, Flawed Algorithms Are Grading Millions of Students' Essays. So I want to read to you some part of this article. E-Rater, do you guys know what E-Rater is? So E-Rater is an automated grading system developed by the Educational Testing Service. So who among you here have ever taken GRE before? A lot of them. Then your essays were probably scored by E-Rater. So E-Rater tended to give students from mainland China lower scores for grammar and mechanics when compared to the GRE test-taking population as a whole. But the engine gave them above average scores for essay length and sophisticated word choice, which resulted in their essays receiving higher overall grades than those assigned by expert human graders. So these engines favor essays by mainland China students more than human graders. On the other hand, African Americans tended to get low marks from E-Rater for grammar, style, and organization, and therefore received below average scores, but when expert humans graded their papers, they often performed substantially better. So the engines also focus heavily on metrics like sentence length, vocabulary, spelling, and subject-verb agreement, the parts of writing that English language learners and other groups are more likely to do differently. The systems are also unable to judge more nuanced aspects of writing, like creativity. So it sounds like these engines are not grading how you think or how you reason about some topic. It just grades how you write it in terms of your sentence length or your word choice and so on. So we definitely need some better tools for this tools that can understand human argumentation better. So the outline for the second part of the lecture, so we're going to cover what is an argument and argument structures. And then we'll move on to argument mining, which is how to identify argument structures, and argument quality, how to measure argument quality automatically. Okay, what is an argument? Based on this definition, an argument is a claim-reason complex consisting of an act of concluding, 2, one or more acts of premising, which assert propositions in favor of the conclusion, and 3, a stated or implicit inference word that indicates that the conclusion follows from the premises. Let's look at some example. I say, Korea is not a police state. This is my conclusion. But this is not an argument because I don't give you any premises that support this conclusion. And I continue to say because, okay, some premises are coming up. The Korean elections in 1948 and 1950 were free and fair. So I'm giving you some premise that supports my conclusion. So now this entire text becomes an argument. Let's look at some terminology. What is proposition? So proposition in logic is a statement proposing an idea that can be true or false. Sometimes a proposition is just called a statement, and the proposition is the basic unit of an argument. So if you look at these examples below, snow is white or snow is green, they're propositions because they have some truth value. But if I say ouch, then it doesn't have any truth value, so it's not a proposition. If I ask you a question, where are we? Then this question also is not proposing any idea that can be true or false. I'm just asking for information. So this is also not a proposition. Similarly, imperatives like open the door doesn't have any truth value, so they're not propositions. We also often see terms like conclusion, claim, premise, evidence often. So what do they mean? So conclusion or claim is a proposition that indicates of what the arguer is trying to convince the reader. On the other hand, premise or evidence is also a proposition, but that provides reason or support for the conclusion. So based on these definitions, we cannot say a certain proposition is by nature a claim or a premise because it depends on its relation to other propositions. So if you look at this example below, I argue that I think Chipotle makes a lot of money. Why do I think so? Because many CMU students go to Chipotle. How do you know? I have at least 5 CMU students who go to Chipotle every day. So this is my argument. They are all propositions, but P2 is a premise in relation to P1 because P2 is supporting P1. But P2 is a conclusion in relation to P3 because P3 supports P2. So this is the some important distinctions between conclusion and premise. There's some argument structures we can use. So maybe one of the best known ones is modus ponens. So modus ponens argument has one conclusion and 2 premises, and one of the premises is a conditional premise. So I say if Harry was born in Bermuda, Harry is a British subject. And my other premise is Harry was actually born in Bermuda. Therefore, Harry is a British subject. This is my conclusion. Done. Modus tollens is similar. It has the same conditional premise, but the other premise and the conclusion are negated. Let's look at some more modern ones. So Tolman structure has more nuanced components. So it first has a datum, which is evidence such as facts, report, etc. And again, you have some claim. So I want to claim that Harry is a British subject, and my datum is Harry was born in Bermuda. So this is just a fact. But then you may ask, how are they related? I mean, why does this datum infer the claim? So here we need some warrant, which is an inferential link between the datum and the claim. So here I say, a man born in Bermuda will generally be a British subject. Then you may ask, why? And then there's this component called backing, which is to justify the warrant. That's true because legal statuses of ABC and legal provisions XYZ show that. There's another component called quantifier, which is to modify the claim depending on the certainty of the claim. So I can say, presumably, Harry is a British subject, or I can say, certainly, Harry is a British subject. And lastly, there's the component called rebuttal. The rebuttal describes some exceptional cases where the claim may not hold true. So if both his parents were aliens, then Harry may not be a British subject. So you're giving some exceptional cases. Okay, let's look at one more example. Walton's argumentation schemes are more recent and very popular. there are common reasoning patterns people use daily. So in argument from sign, the conclusion has the form of A is true, and its premise has the form that A generally causes B, and B is observed now. And that's why A is true. So in this example, I say, I think a bear passed this way. Why? Because here's some bear tracks in the snow. So you can see this kind of reasoning a lot in detective novels based on some observations and some possible causes of these observations. You make some conclusion. In argument from example, the conclusion has the form A is true, and the premise has the form an example case of A, B is true. So I claim that birds can fly. Why? Because pigeons can fly, chickens can fly, ducks can fly, penguins can fly, so birds can fly. So you can see this kind of reasoning a lot in scientific papers where people use observations to make some generalization. In argument from consequence, the conclusion has the form that A should be carried out, and the premise has the form A will yield a positive consequence B. Therefore, A should be carried out. So you'll see this kind of reasoning a lot in policy making. Okay, how about NLP? In NLP, unfortunately, we only use some simplistic notions of support and attack. As in sentiment analysis, in spite of all these different kinds of emotion, we just use positive, negative, and neutral. And similarly, for computational argumentation also, we often use just simple notions of support, attack, or sometimes unrelated. Okay, given these definitions and theoretical frameworks, let's see how we can do argument mining. So argument mining is how to identify argument structure from text automatically. So let's just adopt the simplistic notions of support and attack. So argument mining task usually consists of this pipeline. So first, we're given some argumentative dialogue or monologue, like essays. So in this example, we have this utterance from Marco Rubio. And then our first task, is to extract propositions from this utterance. So the blue boxes on the right, they're propositions extracted from this utterance. And then we identify the relations between propositions automatically, either support or attack, or unrelated. Let's look at the first part, proposition extraction. Often people just segment text into argumentative discourse units. So argument discourse units, or ADUs, is a minimum text span that conveys a proposition. So if you want to extract propositions, or if you want to segment ADUs automatically, then we first need some data to train our model on. So we first annotate text with ADUs. So some annotators, they highlighted individual ADUs in real text. And then we formulate it as a sequence tagging problem, like NER tagging. So for individual words, we assign either B, which is the beginning of an ADU, or I, which is inside of an ADU, or O, which is outside of an ADU. So this is very similar to NER tagging. And then now it becomes just multi-class classification task. Okay, let me ask you a question. What models can we use for this task then? Is sequence tagging. Can you think of any model we learned in class that deals with this sequence data? Sorry? HMMs. Okay, that's a good one. But in this lecture, I'm going to introduce another model very briefly called conditional random fields for sequence tagging. So linear CRF which is a simplified version of CRF, is quite similar to hidden Markov model. Both models have a set of Ys, which is the set of states that you want to predict the values of. And they also have a set of X's, which are the observations. But one of the main differences between the two models is that for CRF, we can define arbitrary feature, f, that at each time point t, it calculates its value using the current state, the previous state, and any observations. So if you think about HMM, at a specific time point t, the only features you can use is the transition probability from the previous state and the emission probability. But using CRF, you can be more flexible and you can make more arbitrary features. We'll see some examples later. Also, if you look at the objective function, and then CRF optimizes the probability of Y given observations, and it is defined as the exponential of a weighted sum of feature values. So if you train this model on your data, then the model will learn optimal weights for your features. So you can look at these feature weights and see which features are important in your prediction task. Okay, let's look at some example features we can use for CRF. Of course, we can use some transition features because some transition between states are very, very unlikely to happen. So the model will assign very negative feature weights for those features. We can use some observation features. Let's look at the first example. F1 takes value 1 if the previous word is a punctuation. Now, this kind of feature is not allowed in HMM because you can see only the current observation. But in CRF, you can define features using any observations. So these are some possible features for this sequence tagging. Now you train the model based on these features, and you have some predicted sequence of tags. So now you have model prediction. Then how can you evaluate the performance of this model? So we can compare it to the gold standard label. And now this is just simple multi-class classification task. So you can just check how accurately the model predicted B, I, and O compared to the gold standard. So you can simply use some metrics like average recall or some other generic metrics for multi-class classification. Okay, now that we have some propositions, particularly two propositions, let's classify the relation as support, attack, or unrelated. So this was in the midterm, and I think many of you were on the right track. So it is logical to first classify instances between unrelated and related. And as many of you mentioned in the exam, the authors of this paper also used word overlap. So the idea is if two propositions have a lot of overlapping words, then they're more likely to be related. But they used only noun overlap. They also used some indicator features of different classes of discourse markers. So if those discourse markers appear in a proposition, then they're likely to be related to each other. So these kind of features are very useful for formal writing, but they are not as useful for informal argumentation because in our daily argumentation, if you pay attention, we don't really use discourse markers a lot. So this is a very challenging problem in argumentation mining. You can use some other features, and again, you don't have to memorize all these features, but it'd be nice to see like what kind of features you can use for this task. Okay, the next step is to classify related pairs into support and attack. And again, as many of you mentioned in the exam, the authors of this paper also use sentiment analysis. They basically check the sentiment consistency or conflict between two propositions. So first, for each proposition, they calculated the sentiment toward different targets. So in this example, the first proposition expresses positive sentiment toward words campers and food. And the second proposition, it expresses positive sentiment toward cooking burgers and potatoes. And since food and cooking are similar concepts, they conclude that, okay, these two propositions have the same sentiment toward the same concept, so they're likely to support each other. Then the question is, how do you know these two concepts are similar? You can use some approach based on word embeddings, or you can use some synonym-based approaches. It's very flexible. On the other hand, in this example, the first proposition expresses positive sentiment toward advertising, whereas the second proposition expresses negative sentiment toward advertising. So you may conclude that, okay, these two propositions are probably attacking each other. So this is how people usually do relation identification. Okay, the last topic of this lecture, argument quality. So how can we measure the quality of an argument automatically? So in this specific task, you're given a prompt and you're given two arguments that are about the same topic. So here the prompt is, should physical education be mandatory in schools? And your task, or your model's task, is to predict which argument is more convincing. So let's do this game here. So I'll give you about 20 seconds, and you read these two arguments and tell me which one do you think is more convincing. Okay, who thinks the first argument is more convincing? Okay, can someone explain why?
It quotes a number that quantifies negative consequence.
Mm-hmm. Okay. Yes?
The right one doesn't really make sense to me.
Okay.
So, the right one isn't a good argument. It's not it's the facts it's using to support its argument are not good. So the left one, just because it has facts to support it, will have to be better.
Okay. One more. Yes.
The one on the left seems to have more fact, and the one on the right is more opinion.
Okay.
The one on the left is better.
Okay. And who thinks the right one is more convincing? No one? You can't see any good things in the second argument?
It's grammatically correct.
It's grammatically correct. That's a good point. That's a typo.
Okay.
Yeah. Of this argument, not my typo. Is the it appeals to emotion.
Which is not necessarily the trademarks of a good argument, but it makes it salient, I guess.
Okay. I mean, appeal to emotion is a very important factor in rhetoric. So that's a good point. I think you guys came up with all good points. So you have some ideas, even unconsciously, about which argument is more convincing. So let's featureize them. So these authors use different features to measure all these criteria. So they used unigrams and bigrams, basic. They measured the formality of the argument using the distribution of POS tags. They also calculated the ratio of exclamation and quotation marks. They calculate the ratio of modal verbs, and they use some external tools to measure the readability of an argument and also spelling errors. So all these things were brought out here. So they use some standard SVM classifier using these features, and without too much detail, their accuracy is 0.78, which is not too bad. Okay, let's look at another test. Finally, we came back to automated essay scoring. So in this task, you're given some prompt or topic, and you're asked to write a short assertion, which is your main stance toward the topic, and then you're asked to justify your assertion. And in this essay, there's 5 grading criteria: grammar error, lack of objectivity, inadequate support, unclear assertion, and unclear justification. And based on these criteria, the essay grader gives you a final score. How can we automate this process? So the authors of this paper, again, used a bunch of features like the number of grammar errors, number of subjectivity indicators, number of definite articles, and so on. And they used some regression models to predict the scores of the 5 criteria based on the features. And then given the 5 scores of these criteria, they used another regression model to predict the final score of the essay. So again, without too much detail, their mean absolute error is 1.03, where scores range from 1 to 6. So it means that on average, the model predicted score is different from the human graded scores by only 1. So it doesn't look that bad, but we should be really careful when we want to use this kind of system for high stakes tests, for example, because this is just an average score. And in reality, for some scores, you'll have a lot bigger discrepancies between the scores given by the model and the human grader. And if you do it wrong, then they may sue you. Okay, to wrap up, today we learned 2 topics: sentiment analysis and computational argumentation. So we covered what is sentiment analysis theoretically, and how to do sentiment analysis using lexicons and machine learning-based approaches. And then for computational argumentation, we looked at what is an argument and argument structures, and how can we do argument mining, and how can we measure argument quality automatically. So this field is very, very applied fields in NLP, and it requires a lot of different tools from different fields of NLP. So I hope that this lecture intrigued you a little bit about this field. So this is it for today, and I'd be happy to take any questions. Any questions? Okay. Thank you.